So let's go to the active antenna and see if we can do bandwidth limitation there. I hope you remember the active antenna needed to have a bandwidth of at least 30 megahertz, but we ended up with about 1 or more than 1 gigahertz. So the question is, can we apply this technique to get more loop gain at a higher frequency and thus making the influence of out of band interference signals smaller. I mean, less intermodulation distortion due to out of band interference. That could be a thing. So here is the amplifier that we discussed with the idealized current mirror in between. And of course, you are working in your own solution with a differential pair. I will have some remarks on that one later. And this is the circuit we used for evaluation of the Phantom Zero. And I hope you remember we could implement a Phantom Zero here by placing a resistor in series with the source R3, and I don't exactly recall the value, but it was a very low ohmic value if we wanted to compensate um, for 1 or 1.5 gigahertz. But now we want to compensate this amplifier. We don't want to compensate this amplifier. We want to limit its bandwidth. We want to limit the bandwidth to 30 megahertz. So let's first look at the picture and discuss what we can expect. So basically, if R3 is not there, if its value is 0, then we only have a two-pole system. So the pole of the input of the second MOS transistor, the capacitance with the current source, which is a pole in the origin, and a pole formed by C2 in series with C1 in parallel with 100 ohm. So as soon as we are going to compensate this amplifier, and this is what we have already seen, and we insert this R3 in the signal path, we break one loop of capacitors, which is basically C1 in parallel with CGS of the first transistor, which was much smaller than CA. But we break the loop, so we introduce a new pole, a third pole. Now you can imagine, and this third pole was located at about the parallel connection of R3 and CGS of the first transistor. Now you can imagine if we increase R3, that this pole is coming to a lower frequency. If we also increase R3, then also the Phantom Zero will go to a lower frequency, and there will be a strong interaction if you would look at the root locus plot. So let's study the effect in SliCap. So we know already that we are going to expect some effect of a third pole, but let's see how it works. And let's also calculate the value of R3 for 30 megahertz bandwidth limitation and study the consequences of that. I did it here and I prepared it. Maybe we go through the file again. It's just exactly the same file as for the Phantom Zero correction. So there's just the checking of the circuit, the page on which I display the data. I calculate the antenna capacitance. No, I didn't calculate it from the model. I just assigned it like 5 PF and the feedback capacitance 2.5 PF and then we calculated here the Phantom Zero, the poles, and the Phantom Zero resistance here. So the Phantom Zero, and define the parameter for the Phantom Zero. That is what we did. And then we can plot the transfer. That has all already been done in the previous demonstration. This is what I added. I set the maximum frequency to Fmax and calculate a value Rmax, which is 1 over 2 pi Fmax times the value of CA. So if I change it in at the beginning of the file, everything will just track. That is the nice thing of this program, of course. If you do it correct, you can type your specs in the beginning, change the specs, and have a new design. So then we have the Bode plots of the bandwidth limitation because I defined this parameter R phantom zero equal to this maximum resistance. And then we get this plot and see what happens, and also plot for this situation a uh, root locus plot as a function of this resistance. So I'm stepping the resistance from the phantom zero value to the maximum value. The nice thing in Python SlideCap is you can do really a root locus plot for many points. Here I do thousands points. It takes some time, but not as long as in a MATLAB version. This is much faster because I calculate it in a different way. You already see some plots on the right side, but I would like to go to the file, the output, because it's easier to scale. So the circuit data. Oh, I must take the good file, of course. The circuit data is, of course, this file, this circuit with exactly as what I demonstrated on the sheet. All values, as you can see, are numeric. So I can do plotting and pole zero analysis, because that can only be done numerically. If you try to do pole zero with symbolic values, it will give you all kind of error messages. So you see, that is why we make this page, to just check if everything is numeric. And for the rest, at this point, I'm not interested in all these numbers, because we have already designed the FETs, we have already designed the noise. We are now just looking at the bandwidth limitation. So we also know the bandwidth is okay, and we want to limit it to 30 kilohertz. So this is not so interesting. And we just go back to the index page and then to the Bode plots. This is the Bode plot after we have compensated. And as I told you, the compensation is not perfect, because we basically get another pole, and this pole affects the compensation. This I didn't show it here, but you could see it in the last in the lecture of the phantom zero discussion. If we increase the phantom zero resistance a little bit, then we can really tune to maximum flat magnitude characteristic. But I hope you remember, the peaking without compensation was from minus 6 dB to 10 dB, and now it is from minus 6 dB, from minus 6 to 0, and now it is from minus 6 to minus 4. So we have only 2 dB peaking left, while it was 4 dB peaking. 6 dB peaking, I guess, yeah, 6 dB peaking it was. So that is the compensation. But now we are going to limit the bandwidth. And let's see what we can expect then. And here is the plot with the bandwidth limitation. And you see we limited the bandwidth, and you see indeed that the bandwidth here is megahertz along the axis. So the bandwidth is the -3, the bandwidth is 30 megahertz. That will be okay. It's automatically calculated. So there are no calculation errors in here. But you see a third pole is becoming to be dominant and becomes complex pair with one pole that was moving to infinity. That's exactly what is happening here. And we have peaking. In the phase characteristic, we can see that the phase still goes in the right direction. This is mostly an indication that the thing is stable. The peaking is not an indication that the thing is unstable, and neither is it an indication for stability. And also a nice smooth uh, decay here is not an indication for stability. You have to go to poles and zeros for this for studying the stability of a system, because you cannot see it from the magnitude characteristics, although many people like to do so. So let's go to the pole zero plots then. And here I just make one plot. One plot, I stepped the phantom zero resistance from its value. You see, it started at 13 ohms to get this 1 gigahertz bandwidth. I think it was about 1 gigahertz, I don't recall exactly. But we need to put 1.1 kilo ohm in it to get 30 megahertz. And if we do so, if we step, then you see what happens with the root locus. So it is not on equal scale, otherwise it would have been a circle. So the imaginary part reaches up to 12 gigahertz and the imaginary part reaches up to plus minus 3. So if we would put this on 6 gigahertz, the real part, then you could find that they turn out to be nice circles. So it starts here almost Butterworth position. The cross is the start position. That was compensated. That was almost Butterworth. And you see, if we increase the phantom zero resistance a little bit, then they will become Butterworth position. And then they go together to the imaginary axis. One goes to the zero, which is at 30 megahertz. You cannot see it so much in the origin here. And the other one, together with the third pole that was far away, now are becoming to be complex and move in a circle around the zero, and they will move basically into the left half plane if you are making too much gain. So that is how the system is now. It is compensated, but we have peaking. You see the complex, the imaginary part is 3 gigahertz and the real part is 1 gigahertz. So we have peaking. We would have a maximum magnitude characteristics if those poles would have been would have had a imaginary part equal to their real part, which is also 1 gigahertz. But they're not. So we have peaking, but it's not a disaster. But usually you don't want this. For example, this means, let's look at the Bode plot. That means that noise in the, let's say, vicinity of, this is 1, 2, 3, of 3 gigahertz. There's the peaking, of course, because there was the imaginary part. That was the magnitude of the complex poles. So noise in the vicinity of the 3 gigahertz will be amplified by the antenna relative to other frequencies, and that is something you usually don't want. So you could say this method of limiting the bandwidth to such an extent from gigahertz to kilohertz to 30 megahertz is really giving some disadvantaged behavior here, but there is more. Maybe you recall the values that we needed to make. We wanted to have some equivalent input noise of 5 nanovolts per meter per square root of hertz, and we had an antenna of 0.5 meters. So at the input of the amplifier, it should be about 2.5 nanovolt per square root of hertz. 2.5 nanovolt per square root of hertz, and we are placing a resistor in series of the signal path of more than 1 kilo ohm. I think it was 1.3 kilo ohm, if I remember well. 1 kilo ohm is nice to remember. 1 kilo ohm is equivalent to 4 nanovolts per square root of hertz. So we are inserting a noise source here in series with the input of 4 nanovolts per square root of hertz. So I would say bandwidth limitation down to this frequency with this low antenna capacitance is no option. Although it is nice to reduce the influence of out-of-band interference signals, we are increasing the noise floor incredibly. We are making it more than 2 times larger. We had about 2.5 nanovolt per square root of hertz, and we add 4. So that is really disastrous. The noise of the resistance R3 becomes dominant in the whole system. We could make R3 smaller, so small that its noise contribution is not longer significant. And then still we can have some bandwidth limitation and still some advantage of having reduction of, I would say, attenuation of out-of-band interference signals. So that is the discussion. You see, there is it is a strong method, but it has its disadvantages. And so one conclusion would be here. It would be easier to do with a larger antenna. With a larger antenna, you get a larger capacitance, which means you need a smaller resistance. And that goes hand in hand. So then you have lower noise and you could have more noise there because you had a larger antenna and a higher gain. So you see how all things can be designed orthogonally, but still at the end you have to check if they really are orthogonal. So here in this case, bandwidth limitation is not orthogonal with noise behavior. There's too much influence if the bandwidth limitation is too strong. That is what I would like to show you. So both the method here is shown and the limitation of the method is shown.